Okie dokie, pause and copy. So. We have some strange limits here. That's roughly what we're saying when we say indeterminate form. Okay, we say I have a limit. In this case, the numerator is approaching 0, because sine of 0 is 0, and also the denominator is approaching 0. Okay, so you have this limit which has, this form here, 0 over 0, and that is a very strange thing. We cannot, from this 0 over 0, we can't determine what the final answer is going to be. So we call this an indeterminate form. So how to resolve these things? You learn some techniques in Cal 1, and we're going to give you further techniques, further mostly involving L'Hospital's rule. So very roughly, what L'Hospital's rule is going to say to us is going to say that we can take this limit. The H indicates I'm going to say L'Hopital's rule. L'Hopital's rule. I'll drop the S, silent S. What am I talking about? You have this rule that allows you to replace the numerator with the derivative of the numerator and replace the denominator with the derivative of the denominator. So this will turn out to be very useful in many cases, and in this case, since these derivatives will be cosines, which will no longer give these zeros. Okay, so that is the L'Hopital's rule in a nutshell. Sometimes you can replace a complicated limit with hopefully a better one. Now you're doing a derivative of the top and the bottom separately. There's no quotient rule happening here. Okay, let's look at the formal statement of L'Hopital's rule. So pause and copy. Okay, there's a bit of a word salad here, but let's focus on certain elements here. Now, here's what I was saying before. In my rectangle, okay, if you have a limit of the type 0 over 0 and infinity over infinity, okay, almost always you can do this. Now, there are some exceptions, as there often are in math, especially in calculus. And I think I will cover one of them. I'll do an example of one of those later on. But for the most part, if you have 0 over 0 or infinity over infinity, then you can do this. What else should I say? So it doesn't have to be, you could also have like minus infinity over infinity. That's okay. Or you could have minus, or, all these permutations are fine. What else? You could also have, if x goes to like 7 plus, if your limit has a certain form, one-sided limit rather. If you have a one-sided limit, this also applies. Okay, let's do some examples. X over e dx. Now the numerator is approaching infinity, and the denominator is approaching infinity. So I can apply L'Hopital's rule, which I do, indicating with an h that I have done so. You don't have to put this h. Another thing you'll notice is that I didn't write anything below my limit. I'm not going to require that you do that. Okay, it's written here. So that's good enough for me. You know what? Because I'm a nice guy, I'll even go one step further. You can just put it like a scripty L there. Maybe that's too nice, but you know what? We're just going to go with that. Okay, I think for the rest, the rest of this chapter, I'll probably put lim, but you can just go with the scripty L to save ink. Okay, what was I talking about? I apply L'Hopital's rule. Now I have resolved my difficulty. Okay, the difficulty was this infinity over infinity. Okay, that is difficulty. I hope you agree that's difficulty. Okay, I can't tell which one of these infinities is going to win. I shouldn't say it that way. I should say like I can't tell which one of these functions is going to win. Okay, they're both approaching infinity, but this guy on top is pulling me towards infinity, pulling the overall fraction to infinity. This guy in the bottom is pulling the overall fraction towards 0. So it's like a tug of war, and we cannot decide from the outset who is going to win. So I'm just trying to convince you that this is indeed a strange situation. But when I apply L'Hopital's rule once, my situation is no longer difficult. Okay, the numerator is 1, and the denominator is going to infinity, so my difficulty is resolved. This limit is definitely 0. Okay, so we're applying L'Hopital's rule until we have resolved our difficulty. Okay, let's go back to our first example. This one's 0 over 0. So I'll apply L'Hopital's rule and get something that is no longer strange. Okay, cosine of 0 is 1. So we've removed our difficulty, so we are done. Okay, a different type of indeterminate form. Now we have what's called an indeterminate product. Okay, you have the x is going to minus infinity, and the exponential is going to 0. This is a indeterminate product, an indeterminate form. Okay, it's just as bad as the 0 over 0 I had above, or the infinity over infinity. I'll try to convince you of that. There is a tendency to just say, oh, anything times 0 is 0. That's not really what we're saying here. Okay, when I write this down on the paper, what I'm saying is that this guy is going to minus infinity. This guy is going to 0. You'll notice they never get there, right? You can never, you're never going to actually achieve this 0. No matter what, if I choose x to be negative a billion, I'm still not going to actually get to 0, right? So we're not saying 0 times something. We're saying this is approaching 0, and this is approaching minus infinity. Who's going to win? Well, I need some more analysis. Okay, the problem here is that L'Hopital's rule requires a fraction. Okay, so I have to take my function here and force it to be a fraction. So I do that by taking the exponential and pulling it downstairs. So I pull it downstairs, the exponent becomes negative. And now, I have something more familiar. Okay, the numerator is going to minus infinity. Denominator is going to plus infinity. Okay, L'Hopital's rule does apply here. And you'll see I apply it. And I have resolved my difficulty. Okay, a limit of the form 1 over minus infinity is definitely 0. Now, I know what you're saying. You're saying, oh, you said that this isn't going to be 0 when you have something of this form. No. I said it is sometimes 0, but not always. So let's see an example where it ends up not being 0. Okay, pause and copy. Okay, x is going to 0 plus, so this is going to 0. And in the thought bubble, or thought cloud, I convince you that the cosecant is going to plus infinity. So we have an indeterminate product. Let's see what happens with this one. I force it into a fraction by taking cosecant and throwing it into the basement where it becomes sine. And now I have, oh, I didn't write that. Now I have something of the form 0 over 0. So I can apply L'Hopital's rule. And just like earlier, the cosines appear, and I am able to resolve this as 19. See? All right, pause, copy, try this exercise. Actually, don't pause. We will pick it up in the next video.